Welcome back to Chem 4300. In this video, we're going to finish up Chapter 18 on the electronic structure of the hydrogen atom. Now, in the previous videos, we derived the energy eigenvalues for the hydrogen atom, and we also derived the quantum numbers that you learned about in high school chemistry. The principal quantum number, N, the azimuthal quantum number, L, the magnetic quantum number, M sub L. And we did that by solving the Schrodinger equation for an electron bound to a positively charged nucleus with an attraction, that's the Coulomb interaction. We also learned that the energy eigenstates can be split into a radial part and an angular part. And the angular part were just the eigenstates of the angular momentum operator. The radial part we were able to derive or work through and show that the differential equation for the radial part was the associated Laguerre differential equation, which have solutions which are the associated Laguerre polynomials. So now we're going to look at that final part, the radial part of the wave function, and get it all normalized, put it together with the angular part, and look at the final solution for the wave function for the hydrogen atom. So, as I said, the solutions for the radial part involve these things called the associated Laguerre polynomials, and we will construct the radial part. And what we have to do is we have to work backwards. If you remember in that derivation, we set it up into a differential equation for a function called u, which was related to the radial part. So now we have to work our way backwards to the radial function as a function of r, the distance between the electron and the nucleus. So this was the solution that we found in terms of the differential equation. That u is related to r by taking u and dividing it by rho, which is another term that we defined. And this gives us this equation here. Simply, we're just taking this term here, L plus 1, and becomes just to the power of L. Then we have to go back with our definition of rho, which was 2 kappa r, and we return this equation into this equation here. Now, remember, our wave functions need to be normalized. The spherical harmonics are already normalized, but we need to normalize this part. So we're going to redefine r by adding in some yet-to-be-determined normalization coefficient here. And now we need to work out what that is. And of course, now you know the procedure. So we're going to integrate this over all values and set it equal to 1. To do this integral, I'm going to define x is equal to 2 kappa n times r. So I'm going to rewrite it this way, where I change my coordinate from r to x. And you can see a little factor that comes in that transformation. And in terms of x, then, my function looks like this with the Laguerre polynomial in here. And so putting it into this integral here, it becomes this integral. Now, I'm just going to look up this integral. There are tabulated integrals for the Laguerre polynomials. And what you find is that integral will be equal to this. And then going back up here, and you can see that there are some differences here. So we have to make 2L plus 2 is equal to k plus 1, and make all these different associations. So we transform that and solving this integral, and we get this result here, which has to be equal to 1. So now we just simply solve for a, and we get our normalization factor here. So now we've completed the task. We'll do one last thing. We're going to redefine the quantity that's analogous to the Bohr radius. Everything's the same, except for instead of the mass electron, we're going to use the reduced mass here. That allows us to redefine kappa n as z over n times that new radius. And that changes this term in the radial part into that term. And so, ta-da, we get our final result, which is the normalized radial part of the hydrogen atom wave function. And again, that's a pretty tedious derivation. I don't ever expect you to, in this class, to be able to derive that from first principles on your own. I just hope that you could follow that derivation to see how we arrived at this result and see how all of those quantum numbers originate for the hydrogen atom. You can find tables of these all over the place, but in the textbook you can find a table. So these are tables of the radial distribution for different values of n and L. And here is n equals 1, n equals 2, n equals 3, with n with L increasing. So L can only be 0 here. Here we have L values of 0 and 1. Here L goes from 0, 1, and 2, and here's L of 0, 1, 2, and 3 for n equals 4. And so you can, this is just the radial part. Now we need to bring this together with the angular part, which is the spherical harmonics, and that will give us our total wave function for the hydrogen atom. Okay. So the quantum numbers n and L are part of this radial function, and of course for the angular part, the spherical harmonics, the quantum numbers L and m sub L are part of this definition. Together, we form our wave function, and we call this an orbital. Not an orbit function, it's called an orbital, and that describes the electron's quote-unquote orbit around the nucleus. Here they are, all tabulated together for the orbitals labeled here, 1s, 2s, 2p, 2p plus or minus 1. Plus or minus 1 means m sub L plus or minus 1. And here are the 3s, 3p, 3d orbitals here. All of those orbital names I'm sure that you recognize. Here are the full wave functions normalized for the hydrogen atom. Again, now at this point, we went from a very difficult derivation to a review of some topics that you've learned for many years ago. So the probability of finding the electron in some volume element is just going to be this term right here. So just taking the wave function with the differential volume element here in spherical coordinates. So what I'm going to do is integrate out all of the angular part here and leave myself with just the radial distribution function. So this describes the probability distribution along the radial dimension. So in other words, from the origin where the nucleus is out, what is the distribution of probability in all directions? So we integrated out the theta and phi part. So this is what's called the radial distribution function, and we'll look at some plots of that here in a second. Before I go to those radial distribution plots, I want to show you some cross sections of the full wave function. So these are plots with, in parentheses here, are n, L, and m sub L. And these are 2D cross sections through a 3D probability distribution. These are through the XZ plane. So you can see all the different orbitals. Here is the 2s orbital, the 3s orbital. Here is the 4s orbital. They're kind of arranged in a little bit, just sort of selected order here. Now, note that the number of radial nodes, so we said earlier, is n minus L minus 1. So the radial nodes, here you see examples, that's a radial node. Here we see for n equals 3, for the 3s orbital, there's one radial node, another radial node. For the 4s orbital, we see 1, 2, 3 radial nodes. And then you see that the radial nodes actually get reduced as L increases. So for 2s, we have one radial node, but for 2p, we lose the radial node. There's no radial node here. And so when you see that here is 3s, there's two radial nodes, but when you get to 3p, then there's only one radial node here. So we're losing radial nodes as L increases. And then, of course, you can see the angular nodes, which is something we've seen before in the classical wave chapter for the spherical harmonics. And you can see that when you have, for example, here's the 3p or 2p, you see there's an angular node here. If you take a more extreme example, go down here. This is the 4 with L equals 3. So that's the, 0, 2, so that's an F orbital. And you can see there's 1, 2, 3 nodes in that guy. Okay, so I'll let you take a look at this and verify that all the nodes' behavior is what you might expect. If we go to look at the radial part of the distribution function, excuse me, you can see that the wave function extends further out as we increase the principal quantum number. This is 1s, 2s, 3s, 4s, 5s. You can see this decay goes just a little bit further out as you continue to increase the principal quantum number. And here you can see in the probability, which is r squared times the radial distribution, the radial wave function squared. that shows very clearly that behavior as it extends out in terms of the probability. Now, another thing to remember, just like the harmonic oscillator, when the total energy exceeds the potential energy, you don't expect there to be any probability in a classical picture, what we call the classical excluded region. That, in this problem, is defined to be R over A mu is greater than 2n squared. So that's what's indicated by this sort of gray region here. You can see this in the plot. And you can see that the probability does extend quite a bit into the classically excluded regions. As you increase the end, there's pretty significant extension out there into that region. The other thing to look at is for a given fixed n, look at the change in the wave functions as you increase L. So this is 5s, 5p, 5d, 5f, and 5g. And you can see one thing that's interesting is that for the S states, they're the only wave function that has a high finite value at the origin. So they have a non-zero value at the origin here, so you can see. But then as soon as you add angular momentum, then that goes to 0 or a very small number. So the wave function maximum, you can see that as L increases, the maximum of the wave function gets pushed further and further and further and further out away from the nucleus. And again, we talked about that earlier. That's due to this centrifugal term, which adds sort of this potential that makes it look like it's a repulsion that pushes it away as the angular momentum increases. Now, one thing we can do with these orbitals is that we can take linear combinations of them if they're degenerate, and they're all going to be solutions to the wave equation. And one thing that's hard to deal with sometimes when you're trying to look at these orbitals is the fact that some of them are complex. All the ones with m sub L are going to be complex wave functions. But you can take linear combinations of these m and minus m sub L's together, and you will form real functions. And this is sort of something that you've seen in all your textbooks. You'll see, instead of p minus 1 and p minus 1 and p plus 1 orbitals plotted, they'll plot px and py, which are just linear combinations of p plus 1 and p minus 1. But these are real functions that are easier to plot. You don't have to try to plot a complex variable in 3D. Now you're plotting a real variable in 3D, and that would be px and py. And these are valid solutions too, because again, they're linear combinations of these two orbitals. Linear combinations of solutions will also be solutions to the wave function, and these are degenerate in energy. So these will all be perfectly valid solutions for describing that the wave function in the xy plane, so to speak. So these are linear combinations. If these guys are stationary states, then obviously the linear combination will be a stationary state. You'll see later that these linear combinations defining px, py, pz, and so on, dx x squared minus y squared, we'll see in a bit, are all important for understanding bonding in certain situations. And you see these pictures in pretty much every elementary chemistry textbook for these orbitals. So here's an example I pulled off the web at a really cool site called Orbitron. You can, on the PDF, you can click on that and you'll go to that website here. And here's some cool pictures where you can visualize these. Again, now you've probably seen many of these before. The d orbitals, again, you can make linear combinations of the m and the m plus and minus values of the m sub L's, and you can get all the combinations that you recognize, dz squared, dxz, dx squared minus y squared, and so on. They're all defined here. And again, go back to the Orbitron website. You can see some really nice 3D illustrations of these different types of d orbitals, which I'm sure you're familiar with. And I'll leave this last one for you to play with. This is a link here that takes you to a really cool web app by Paul Falstad, where you can interactively work with these 3D orbitals and rotate them around and see how they look. So that's it for this chapter. We finished the hydrogen atom, and next we will start looking at another quantum number that was missed in this treatment, which is the spin quantum number, and we'll look at how that was discovered and how we're going to incorporate that into our picture in the next chapter.